Hello, welcome back to Computer Science 3200. So today we are at the second of two lectures on game theory. And I find game theory really fun. I find that it makes you think about things in different ways. And ideally, you take those lessons that you learned from game theory and try to apply them a little bit into real world decision making. So today's lecture is going to be all about Nash equilibrium, essentially. And Nash equilibrium, now that you've been given the intro to game theory, is actually quite an easy concept to understand. So we're going to go over that, and that won't actually take very long, but the remainder of the class time is going to be devoted to playing a couple of games. So the first game here is called the investment game. So there's the link to the forum where you're all going to go and you're all going to answer. But let's look at the investment game. So in the investment game, you're going to pick one of the following options. Invest or don't invest. Okay, so you're just picking invest or don't invest. If you choose invest and 80% or more people chose invest, you gain $100. But if you chose invest and less than 80% of people chose invest, you lose $100. However, if you don't invest, you neither gain or lose anything. Okay? So that's the game. And it closely resembles economic games that we play in real life. So here you have the properties of this game. So please click on that forum and fill it out, and I'll go over the results shortly. So the players are everyone in the class. The strategy set is either invest $100 or don't invest. Now, we're not playing with real money here, so maybe your choices would be different if you were playing with real money. But let's just pretend, that play it with the knowledge that there is some sort of payoff, right? Because if you don't care, then you just don't play, I guess. So the payoffs are, if you don't invest, you gain or lose nothing. If you invested, then if more than 80% of people invested, you gain money. And if fewer invested than 80%, you lose money. And what this does is it kind of mimics a lot of things that happen in real life. Okay? So I want someone out there in the chat, if they can, come up with an example of a real life scenario that is not economics, that also follows the rules of the investment game. See if you can come up with one. So it's obvious that the stock market operates on a policy like this. The success of a company operates on stuff like this, right? If a bunch of people invest in a cryptocurrency, they want to buy the crypto so the price goes up, right? If a lot of people, now this 80% number is just some number that I chose. That could be an arbitrary number. So just keep in mind that this can apply to non-financial situations as well. So, okay, I haven't had any examples out there yet, but let me describe one. How about a party? Have you ever had a situation where you were trying to get a group of people together? And this happened so often back, when Facebook was kind of new, and I know I'm dating myself with this. What would happen is that, you'd have an event for a party, and what people would, they'd go to see who was going before they said if they were going, right? So if everyone just said they were going without looking at who was going, it'd be a great party. But if only 2 or 3 people said they were going, then more and more people said they wouldn't be going, and it would be a worse party, right? So in situations that are not strictly economical, like gatherings of people or having fun or relationships or whatever, the investment game also applies. So what we're going to do now is I've given you enough time to fill that out, and I've gotten 33 responses, so that's cool. So let's look at those 33 responses and see what happened. Okay. Oh dear. Look at what happened. Free money was lost, right? So 67.6% of people chose to invest, and 32.4% of people chose not to invest. Okay, so this varies wildly depending on the number 80%. I suspect if this was 50%, you've probably have 100% of people investing, right? If it was 100%, you might have 0% of people investing. And there's various reasons, so just type out there in the chat why you chose invest or not invest, and I'll read out a few of those and I'll go through those different logics. Because I'm always, especially from the don't invest people, why did you not want to invest? When the investing people will say, hey, if everyone had just invested, we'd all get $100, right? So one person out there says, I chose not to invest because 80% seemed really high, right? Now, ideally, the percentage shouldn't matter, right? You should just invest and get your money, because this is not the same as like a stock where it might go up or it might not go up. It's just, hey, if everyone invests, everyone doubles their monies. All right. Some people said, I thought most people would invest and I wanted to make it fun. Invest seemed like the option everyone would choose since we all knew the rules. Getting double returns for doing nothing. Invest. I invested because I thought everyone would want maximum gains. Someone said, I gain nothing, yet I lose nothing. If everyone invested, we would get money. So there's all sorts of different reasons why people would choose invest or don't invest, right? Some people are just risk averse. They will always take the option that gains them a little bit rather than the risk of possibly losing something, okay? So this just goes to show that there's different people out there. There's different people out there with different motivations. Someone else said it's not real money. Yeah, of course, it's not real money. I can't force you to pay up $100. But pretend that this is an exam question, and instead of $100, you might get bonus marks. Okay? Just pretend that might happen. So there's interesting situations that can arise with this, and I love this question because it really makes you think about how people think and how people work. Okay, so that was just an exercise. There's no right or wrong answer to that question, okay? But we will be able to analyze it a little better toward the end of the course, or at the end of the lecture. Okay, so let's go back to the slides here now. And we're going to talk about the number choosing game that we had last time. So last time we played a game called Choosing Numbers. Everyone in the class chose a number between 1 and 100, and secretly and simultaneously, right? And what we did was we calculated the average of all of those choices, and then we said the winner will be the person closest to 2/3 of the average number chosen. And here were the results of that last time. Now let me move myself over a little bit. So we had 34 numbers that were chosen. The average of those choices was 28.76, and 2/3 of that average was 19.7. So there were, or 19.17. So there was nobody who chose 19. So the people who won were the people who chose 20. Now, I didn't collect names just because I didn't want personal information to be online, but if you chose 20, then good for you. You ended up winning that game. Let's talk about the numbers game from a game theoretical point of view now, knowing what we know about game theory from last time. So, are there dominated strategies in the numbers game? Think about that and answer it in the chat. Are there dominated strategies in the numbers game? So let's remember our definition of a dominated strategy. Is there any number that you can choose that the choice of a different number will always do strictly better than your choice of that original number? So is there a number X such that, now if you took this class before, don't answer questions, okay? Let's just let people, I know there's some people who took the class before who were tuning in. Don't let other people, okay. So list some of those numbers, if there are more than one of them, in the chat of what are the dominated strategies. Let's actually think about this name. Oh, great. So there's people out there using their noggins, and 3 people in a row instantly said greater than 66. Let's look at that. That's a good answer. So let's just say, let's work with the highest possible number. So if every single person in the class chose 100, then the average of those would be 100, and 2/3 of that average would be 67. Okay? So that means that the highest possible 2/3 of the average is 67. Meaning that everything, so people are saying greater than 66, I would say greater than 67 just because we round up. But everything between 68 and 100 inclusive, by mathematical definition of the problem, is going to be a worse choice than 67. Because if you choose 67, mathematically, you're going to be closer to 2/3 of the average than any of these. Okay? So, if I ask you on an exam what the dominated strategies are and why, it's because if you choose any number from 68 to 100, 67 is just a better choice. Okay? It's just better. You can't do better than 67 by picking above 67. But can we keep going with this? Well, first of all, let's look back at what our choices had been. Oops. So let's see what people chose. Someone chose a 61. So I will, for full transparency, 2 people chose 100 and 5 people chose 69, and I deleted all of those. Okay, but the rest of them are in here because I said I was going to delete the obvious trolls. All right, so we look through, there's a 60, a 61, a 71, okay? So the person who chose 71 didn't know about dominated strategies or didn't apply their knowledge of dominated strategies correctly to this game. Or didn't care, right? So, can we keep going with this logic? Let's talk about rational players. What would a rational player do if they had identified a dominated strategy? Well, ideally, they're not going to play a dominated strategy. So if you think that everyone applies this logic, then the highest number that anyone can now pick is 67. So now the strategy set is no longer 1 to 100, it's 1 to 67, right? So everyone, let's say everyone picks the maximum value, so everyone's going to pick 67. So the average is now 67, but 2/3 of the average is 45. Okay, you can see where we're going now. So once we delete 68 to 100, because they're dominated, now 46 to 67 become dominated. And they're dominated by the choice of 45, right? And so what's going to happen here? Well, we could keep repeating this all the way down to 1, right? Because eventually, every single number, if we assume rational agents that do not play dominated strategies, then this process will keep repeating down to 1. All right. So here's the rationality chain within this system that we've just created. So 68 to 100 are going to be eliminated because they're dominated strategies if we just assume that everyone applied their rational decision making once. Okay, so they applied it once. They said, oh, okay, well, 67 is the maximum number I should choose. So they've eliminated all these by the rational choice. However, now we know that 45, right, should be the highest number that we should choose. And that's by us being rational and knowing that other people are rational. Then that goes down to 31 to 45. They get deleted because we're rational. We know others are rational. And we know that others know that others are rational. Okay? And this gets repeated and repeated and repeated. So this is sort of that common, in common parlance, if you will, like I know that you know that I know, blah, blah, blah. And so knowing that your opponents are rational or not, or their level of game theory knowledge may affect your choice in this game. All right. So knowing all that, let's go back and let's play the numbers game again. So here's a link to numbers game number 2. And I want to see how people do. And again, please don't troll. Like, I'm just going to delete them. So it's a waste of your time if you troll this. Okay? So someone asked there, what does this have to do with AI? Well, it has to do with decision making. And this is leading into Nash equilibria, which will lead into something in our next lecture. So this is all the story of types of artificial intelligence and how they came to be and why we can mathematically show that we might want to choose these methods. So I'm getting some responses here. I'm going to wait a minute or so to see these responses. Someone said, I can't see the link. Can you not see it in the chat? I just posted it again. 20 people can see it. All right, your chat is blank for some reason. I recommend you refresh the page because it's not playing for other people. Okay, we're up to 24. If we get to 30, I'll stop. Or 30 seconds from now. So if you're watching on YouTube, you can fast forward like 20 seconds. Ten, 9, 8, 7. All right, let's just look at it. Okay, here are our responses. And now what I'm going to do is I'm going to create a spreadsheet of those responses. Google Forms are amazing, by the way. Okie dokie. And here's what we have. Let's zoom out a little bit. And now what we're going to do is we're going to have a bunch of people screaming at their monitors. But that's okay. Welcome to real life, screaming at the decisions of other people. We're going to look at the average here. Now this is going to be 2/3 times that average. Okay. So, even though we just explained how one level of rationality eliminates 78 as being dominated by other things, there's always going to be trolls, right? There are just trolls or people who don't understand or people who aren't listening. So we got a 78. Then we got some 55s, some 45s, some 51s. Those people don't believe in the second level, right, of this game. Now, I suspect that if I had $1 million on the line, this number would be lower. But the point here isn't that there's a right or a wrong answer. It's just that how you believe other people will perform in this game. It's like this weird groupthink where you know that the chain of rationality leads down to 1 being the only non-dominated strategy, right? So you might put down 1, which several people did, but a level above that is sort of the meta of the game where you realize that other people may not think that far ahead. Therefore, they're going to put in something higher. Therefore, if you choose 1, you're no longer going to win. So now you have to choose a higher number, which drives up the average even more, right? Excuse me. And we also have people in the chat saying, I chose 20 because it won last time. All right, that's fine. You're using previous data to machine learn to see what you should predict the next answer would be. That's another strategy. So this is just It's not saying anyone here is right or wrong. I mean, maybe this 78 could be, we could say that's wrong because it's like above the first level of rationality. But what we see as I play this game more and more and more times in a class is that the number does end up going down, right? It goes down and down and down, usually stops in the single digits somewhere, never fully gets to 1. Now, I've never had like real money on the line, and I suspect it would get closer and closer to 1 as the level of money increased, but, you know, that's all you can do. However, I have asked it on an exam for a bonus point, and the average was still like 13. So that'll tell you about the way people think. All right, well, let's go back here. That was interesting. I like playing the numbers game. So the numbers game just goes to show you that here's the life lesson. Here's the life lesson. Even though people know what they probably should do, they don't do it because of what they think other people will do. Right? So they're kind of out for themselves, which is fine as an evolutionary strategy. However, probably doesn't win the game very often, right? Or it skews the results of the game. If everyone just got along, then everyone would get along. But if one person's a jerk, then someone's got to be a jerk to the jerk, and then there's a lot of jerks, right? So it's just interesting. Not to tie that too far into philosophy, but I think it's an interesting thought experiment. All right. Let's get back into the lecture portion now that we've played those 2 games. And let's get back to the matrix games that we played last time and this idea of best responses. So, the best responses... I'm going to try to get my laser pointer back. A best response is the best that you can do given your belief about what other people are doing. Okay? So, we looked at this last time. We talked about greedy players and caring players, and we made their little matrix here of possible payoffs, and we saw that, like, as the greedy player, right? So if we're the greedy player, we fix our choice of alpha for the other player, or their choice of alpha. We see that alpha is best for us. We fix their choice of beta. We see that alpha is best for us. So alpha dominates beta because no matter what, it's going to do better. Okay? Now, we saw that if we switched it, and if you're confused by this, just go back and watch the last lecture. I'm not going to repeat anything. We reversed this by switching the caring player over here and trying to see if the caring player had a dominated strategy, right? So if we fix the greedy player's strategy, then alpha for us, or fix the greedy player strategy to alpha, alpha for us is better. If we fix the greedy player strategy to beta, then beta for us is better, right? But we knew that for the greedy player, alpha dominates beta. So that means we're pretty sure if greedy is rational that they're going to choose alpha. So our choice should be to choose the best response to alpha. So we have a greedy selection, which is we just look at the greedy person's alpha. Then we choose our alpha because it's better than our choice of beta. So sometimes it's better to like put ourselves in the shoes of others in order to make our decision, even though we don't strictly have a dominated strategy for ourselves. So let's talk about Nash equilibrium. So if you've ever watched the movie A Beautiful Mind, that's all about John Nash and Nash equilibrium. I highly recommend that movie. Little dramatized, but you know, for a movie about math, you've got to put some drama in it or no one will watch it, right? So Nash equilibrium means a strategy profile. So remember, a strategy profile is just a choice that everyone has made, okay? So greedy has chosen alpha, caring has chosen beta. That's a strategy profile. It means a selection of actions for each player in the game. So a strategy profile is a Nash equilibrium if, for each player, their choice is a best response to the other player's choices. All right. So what the hell does that mean? It's way easier to understand this visually than it is through a wall of text. However, our motivations for a Nash equilibrium are that why would we want to play a strategy that's part of a Nash equilibrium? Well, A, we can mathematically have no regrets about our choice. So this means that if we hold the strategies of everyone else fixed, no individual player has any incentive to deviate. And what this means is, if you have choices that form a Nash equilibrium, if any single person picked something different, they would do strictly worse. So, if the Nash equilibrium, if their choice is part of a Nash equilibrium, then that choice is the best choice that they could make. They cannot gain by switching their choice. It's mathematically impossible. So you would have no regrets about your choice because it's the best choice given what everyone else has chosen. It's also self-fulfilling. So if everyone believes that everyone else is going to play the Nash equilibrium, right? So if I know everyone else is going to play a Nash equilibrium, then I should be part of that Nash equilibrium, because if I don't, then I'm doing worse than I could be doing, right? So it's self-fulfilling, meaning the more people think that everyone else will behave in this rational way, the more people will also behave in that rational way. So let's look at an example of how we would calculate a Nash equilibrium. And it's very easy, okay? It will be, I'm telling you, that on your exam, either the midterm or the final or both, you will be given a matrix and you will have to calculate a Nash equilibrium, okay? Someone out there is talking about, they're asking questions that were answered in the previous lecture. So if you have questions that I'm not answering, it's because they were answered in the previous lecture, which you probably didn't attend. And I'm not spending all that time explaining again. So here's how to calculate a Nash equilibrium. It's easy to do, and it will be on the exam, okay? So let's say we have player 1 and player 2. The player 1's choices are up, middle, and down. Player 2's choices are left, center, and right. They're just, let's say we're like doing like a soccer shootout or something. I don't know. But they're just directions in order to make it not just like 1, 2, 3 and 1, 2, 3. They differentiate it somehow. So what we're going to do is, for every choice of every player, we're going to calculate the best response of the opponent, okay? Or the other player. So how we denote that is player 2 has a choice of L. We're going to calculate the best response of player 1 to L. That's what this syntax here means, okay? So the best response of player 1 to L would be the action that produces the highest value in the middle, on the left-hand side of this. So if we look at player 1's possible responses to L, up will give them 0, middle will give them 4, down will give them 3. Okay? So the best response of player 1 to L is to choose middle. Okay. Now, if we look at center, what is the best response of player 1 to center? Type it out there in the chat. I just want to make sure you're following along, because you should be able to calculate that best response given the knowledge that you have now. All right. Everyone is choosing up, which is correct, because up will give a 4, middle will give a 0, and down will give a 3. Perfect. Awesome. People are paying attention. That's great. And the best response of player 1 to right is down, right? Because that's a 6. Now we do the same thing, but we want to do it for the other player, okay? So what is the best response for player 2 to player 1 choosing up? Well, we just go through, and now we're looking at the second number, because the second number is the payoff for player 2, okay? So we've got 4 by choosing L, 0 by choosing C, and 3 by choosing R, and so we've got L. Oh, that font is a bit hard to see, but it's a green 4 over here. Next, what is the best response of player 2 to player 1 choosing middle? Well, that's going to be center because you get a 4 from that. And the best response of player 2 to down is right. Okay? So, what is the Nash equilibrium here? In order to find the Nash equilibrium, it's the strategy profile where each player is best responding to each other. So what we would do in this situation of a two-player game with this matrix in the way that we've done it is we have recorded where the best responses are, and if there's any single cell that contains all best responses, then that is the Nash equilibrium. So here we can see that this was a best response for player 1, this was a best response for player 2. So this cell has only best responses. And look at our definition of Nash equilibrium again. A strategy profile is a Nash equilibrium if for each player, their choice is the best response to the other player's choices. So right here, we have that the Nash equilibrium is down right. Now, remember when you're answering questions about Nash equilibrium, or when you're thinking about Nash equilibrium in your head, there's a very important concept that is not intuitive. A Nash equilibrium is not the best possible action for one player. Okay? A Nash equilibrium does not say that the choice you should make as player 1 is down. It does not say the choice that you should make for player 2 is right. It doesn't say anything about the overall best possible choice that you should make. It just says that here at down right, both players are best responding to each other. And so if any player fixed the action of the other player, so right now we have down and we have right. Let's pretend that we're player 1. So player 2 has chosen right. If we choose anything but down, we're going to do worse. Okay? That's one of the definitions of a Nash equilibrium. Is that here, or it's one of the corollaries of a Nash equilibrium, is that when you find the Nash equilibrium, we know that all players are best responding to each other, so no single player would gain by changing their choice. Now, it may be the case that if all players change their mind, they would gain. But it means that if you fix the actions of everyone else and change only your choice, then you will not gain. Okay? And that's kind of weird to wrap your head around that. So just make sure that if I ask you about what the Nash equilibrium is, I've seen on exams, people will say the Nash equilibrium is player 2 choosing right. Or the best action is player 1 choosing down. That is not the case, all right? Not the case whatsoever. Someone said that we can consider player 1 and player 2 are cooperative in this case. Absolutely not. Do not think in that way whatsoever. They are not cooperating. Because there could be another Nash equilibrium that gives them both 1,000,000. Okay? And has nothing to do with this Nash equilibrium. So please don't think of it in terms of cooperation. It's saying that, and think of this in terms of maybe there's 100 people playing the game, right? If there's 100 people playing, this matrix would be 100 dimensions. So I obviously can't visualize that. But just picture there's 100 people playing. And what it means for the Nash equilibrium is that no single person could do better if they chose something else. All right? So he's not cooperating with anyone. It's just saying that if he chose something else or she chose something else, then they would not do better. Okay? So a Nash equilibrium is a set of choices. It's not a single action by anybody. And I'm repeating that so much because every year it's misunderstood. So a Nash equilibrium is a set of strategies. It's a set of choices for everybody. Okay. Let's do another example. So let's do we'll step through this one a little bit quicker. So what is the best response for player 1 to L? It's M. What is the best response of player 1 to C? It's also M. What is the best response of player 1 to R? It's D. Okay? Now we go the opposite direction. What is the best response for player 2 to player 1 choosing up? There's two best responses this time. Okay? There does not necessarily have to be a single best response. So when you're going through, what I do when I'm doing this is I circle all the best responses. So here I would circle this one and I would circle that one. Okay? Because on an exam, you can't like change the color of the text on the paper. What's the best response of player 2 to M? That's C. And what is the best response of player 1 to R? Or to D, it's R. Okay? So where is the Nash equilibrium in this case? Type out where the Nash equilibrium is in the chat, please. I'm just asking this question. All right. So we got a bunch of people saying downright. Okay. I've intentionally phrased my question a little bit misleading so that you'll remember this lesson. And the lesson is there can be multiple Nash equilibria. Okay? So if I asked you on an exam, where are the Nash equilibria in this case, it is both of these. So it's MC and it's DR. Okay? Now, you're thinking to yourself, yeah, but DR is better because both people do better, right? Now, it may be the case that it's preferable for both players to choose D and R versus M and C, but that has nothing to do with the fact that both of them are Nash equilibria. Okay? And again, the reason for that is because if you fix the actions of all the other players in the Nash equilibria, you cannot gain anything by deviating from that. All right? So for example, let's say we fixed in this Nash equilibria, M and C, if we fix the M for player 1, player 2 can't do any better. Right? Because if they chose L, they'd do worse than 2 with a 1. If they chose R, they'd do worse than 2 with a 0. Right? And similarly, player 1 could not do any better than C because if they chose up, they'd go to 2. If they chose down, they'd go to 1. So a Nash equilibrium is a set of strategies. So the two Nash equilibria are right here. Okay. So you can kind of put together now that there's this relationship between Nash equilibria and dominance. So in our first example that we were looking at, alpha strictly dominated beta. Okay? Let's find the Nash equilibria here. So we have a best response here, we have a best response here, we have a best response here, and we have a best response here. And so the Nash equilibria would be at alpha, alpha, and no strictly dominated strategy can ever be played in a Nash equilibrium. That's really strong. So it means that we're never playing a strictly dominated strategy. And more than one Nash equilibria can exist in a game. So in this trivial example over here, we have two best responses for alpha, alpha. We have two best responses for beta, beta. And so alpha, alpha, and beta, beta are the two Nash equilibria for this game. So weakly dominated strategies can be chosen in a Nash equilibria, but no player can do strictly better by changing their strategy. Okay? So, what do I have here? I changed the rules for this, so let me, I'm putting it back to the rules that were on the first slide. Give me a sec. Jeez, excuse me. Got the hiccups. All right. So for the investment game, jeez. It's all right, doing it live here. So for the investment game, remember, The strategy set was invest or don't invest. If 80% of people invested, you gained $100. If not, then you lost $100. So, tell me out there, what is the Nash equilibria, or possibly what are the Nash equilibria for the investment game? Okay? Now think about this from the point of view of everyone else, like it's a choice for everybody. All right? So if I ask you what the Nash equilibrium for the investment game is on the exam, and you say, me choosing to invest is the Nash equilibrium, that is incorrect. Because you have to say what the choices of everybody are in order to properly define the Nash equilibrium. It's a choice for everybody. Okay? And how would you come up with that? Well, you fix a strategy for everybody, and you ask yourself, could you do better by changing? And if the answer is no, then it's a Nash equilibria. So I've got some answers out in the chat that are correct. And the two answers are either nobody invests or everyone invests. Okay? So that is Nash equilibria as far as we want to take it. Okay? You could do PhD thesis on this stuff. It's the Nash equilibria for matrix games. As we look forward, what we're going to do is we have now motivated why we would want to play a Nash equilibria. Let's look at these games. The games that we're playing, okay, are one choice games, like rock, paper, scissors, like a soccer shootout. They're just one choice where you make a choice. What if we have a game like tic-tac-toe? What if we have a game like chess that has multiple moves in a row? Okay? In that case, so these are called matrix games. They're called matrix games because the payoffs can be determined by a matrix. If we have games that have multiple choices in a row, those are called stacked matrix games. I am not going to get into the representation of stacked matrix games, but needless to say, there are algorithms out there. It's kind of a nested matrix. Like if you do this and I do this and you do this, right? There are algorithms out there that can mathematically solve the Nash equilibrium for matrix games, but they take a very long time to run, okay? What we're going to do now, going forward, is we're going to come back to search algorithms, and we're going to show you, because the Nash equilibria for large games like chess or checkers or Connect 4 or stuff like that, because the calculation would take too long, what we want to do instead of like calculating the exact Nash equilibria is let's come up with an algorithm that lets us approximate the Nash equilibria via search. And that ends up being the minimax search algorithm, okay? And that's what we're going to talk about in the next lecture. And wow, the last time I gave that lecture, it took a lot longer. But that's really all I have to talk about for this lecture. So let's look a little bit at the class schedule. I mean, we could play the numbers game again, but I feel like you've sort of, you got it at this point. What I was trying to say, at least. So that's the Nash equilibria. And that's how you use it, and that's how you are going to learn how to calculate it, answer the question on the exam, and then forget about it, right? That's what everyone does. All right. So you are still working on assignment 2 at this point in the course. There is no lecture on Tuesday. So please go out and just work on assignment 2. Assignment 2 has lots of stuff to do. If you have not downloaded and at least started assignment 2 yet, you are behind. Assignment 2 is a lot of work, okay? But working on assignment 2 also prepares for the midterm. On the 14th, 1 week from today, that's when assignment 2 is due, and when I am going over minimax, alpha, beta, and assignment 3. Now, I understand that overlaps with the midterm. However, it's basically the midterm is sort of stuff that was in the lectures and stuff that was on the assignment. So doing your assignments is studying for the midterm. And I'm also giving you the 15th. So there's this rescheduled Tuesday. So the midterm break Tuesday is actually on the following Friday, but I'm just saying there's no class for that day. And so just go study or work on the assignment. Okay. So this lecture, I'm just giving you this lecture off, and there's no lecture in the next class either. So just keep that in mind when you come to attend the lectures and there's nothing there. That's why. And again, I'm available on Discord if you have any problems with assignment 2. So please don't be afraid to ask that. And we're going to be doing a Connect 4 AI for assignment 3 using minimax search and alpha beta pruning. And all of that is built on the game theory stuff that we just learned. Okay, let me answer a couple of questions here. What is the structure of the midterm going to be? The structure of the midterm is calculations of things like Nash equilibria, calculations of things like a minimax search tree, which we'll go over in a future lecture, definitions of stuff. I could give you environments, you give me their properties. I ask you about algorithms. You may have to regurgitate an algorithm or two for me. It's essentially all calculating or long answer questions. However, none of the calculations will require a calculator. Okay? They'll all be at the very most difficult adding integers under 100. Okay? And any answer that may have a fraction you give in fractional amounts. People have been asking about the grades for assignment 1. Unfortunately, there was just a bureaucratic mess up with signing the TAs up at the beginning of the course, so it has been delayed a little bit. So I usually like to have the marks out as soon as possible, but assignment 1 grades will be out as soon as possible within the next few days, ideally. So they're not out yet. I apologize for that. That was kind of out of my hands. And someone said, is the final exam multiple choice? Nope. Multiple choice does not teach you anything except how to try and guess patterns in the data. So none of my exams are ever multiple choice. You actually have to understand stuff and write out your thoughts. Do we get a solution for assignment 1? Nope. The solution is in the slides. All you had to do was translate it to JavaScript. I cannot give out solutions for my assignments because they will be on Russian assignment selling websites within the hour. It has happened. It will never happen again. I'm sick of sending DMCA takedown notices and failing people because of that. I don't know what this person is spamming, but they won't be spamming it any longer. Is there any specific topics we should concentrate more on? Yeah, no. I'm going to not answer those questions now. I'm going to wait until this lecture, and I'll put out something on D2L about what to study for, okay? But basically, here's the rule. If it was in a slide, if it came out of my mouth during a lecture, or if you had to program it for an assignment, it can be asked on an exam. I will not ask any specific JavaScript stuff, okay? That's really not that scary because a lot of profs out there will say, go read chapters 1 to 5 and any of that stuff could be on the exam. That's not how I operate. I'm telling you exactly what's going to be on the exam. If I told you the questions, you wouldn't have to learn. So you have to learn all the stuff in order to be able to answer it, right? And look, there's 10 lectures. It's not that much material for a midterm. It's not that bad. If you did the assignments, you should be fine. All right. Cool. Well, I'm going to stop the lecture there. I will not see you on Tuesday because there is a break, but I will see you in the next lecture, lecture 10, on the 14th. So have a good one until then, and thanks for tuning in.